Okay, in this example we have a basic Atwood's machine, which is just a name for a device that has two masses of equal, or in this case unequal mass, hanging to either side of a pulley, both masses hanging vertically. So we see here that we have the two weights suspended on each side, as I said, and it's shown that they don't have equal mass. So that, as it says, the problem states, the system will not remain at rest. So we'll see that, but you can take a minute and think about why that would be the case. It's also not going to move with constant velocity. Okay? In other words, the system is going to accelerate. In this case, we'll consider mass 1 to have 2.5 kilograms. Okay, so let's write that in. So here we have 2.50 kilograms. Okay, and mass 2, the heavier mass, is 7.40 kilograms. So 7.40 kilograms. Okay. All right. So those will come up in our calculations. And the question is, what will be the direction of acceleration of weight m1? And we are assuming that the pulley and the string are massless. Okay. So basically what we have here is an ideal, which is shorthand for frictionless, massless pulley. Okay. And if you want to see the effects that mass have on a pulley, look at problems that involve rotational dynamics. Okay, but here we're just dealing with translational dynamics. All right, so let's draw the forces and accelerations on our free bodies. So we have two free bodies in the system, M1 and M2. So we'll start with M1. So we have an upward force acting on M1. That is our tension force. And we also have a downward force, which is the gravitational force. Okay, so I'll draw it like this. Actually, no, here, I'll make it like this. Okay, and that is F sub G1. Okay, and then we have a tension force here as well, and a downward force like so. Okay, and that one is F G2. So what I've attempted to do here is draw the relative sizes of the forces, knowing some background about the problem. So one thing is I've drawn the two tensions as the same size. That's because they are equal in magnitude. I've drawn the gravitational force acting on M1 as a smaller vector than the gravitational force acting on M2, which makes sense because the gravitational force is just mg and M2 is larger. But also notice that the magnitude of the gravitational force 2 is larger than the tension force. Well, that's what's driving the system. That is because we know that it has to be greater, because what's going to happen is the motion is going to be down, right? M2 is going to move down while M1 is pulled up. And so there has to be that imbalance in the sizes of the forces. We don't know what the tension force is yet, but we still will expect that imbalance. Okay? So we define our coordinates. Okay? So we're going to define positive y as upwards. We don't have to worry about the x direction. And I'm going to draw the directions of accelerations. Okay? So we're going to have an acceleration for 1 that's going to be in the positive direction. And again, I'm just following my intuition here, right, about what happens in the real world. And then A2 is going to move down. Okay? Okay. So, first of all, let's state what I said before. We know that tension force acting on M1 and M2 is the same because the pulley is massless. Okay? And that's one of the rules that we have to know about massless pulleys, that the tension on either side of a massless pulley is always the same. Okay? All right. And furthermore, we have that A1 equals A2 equals A. Okay, and one thing I want to do in my free body diagram, which I haven't, is clearly make it clear that all the forces are vectors, and they have their little vector notation, and also the accelerations are vectors as well. Right? Besides just drawing the direction and relative magnitude, I just want the notation to show the vectors. So over here, I'm talking about the scalar quantities, and which is obvious because obviously the directions are different, but in terms of magnitude, they're all the same. And why? Because the string, so all the accelerations are equal, or both the accelerations are equal, because the string is not stretchable. Okay, so any rigid, non-stretchable string or negligible, elasticity, negligible stretchability is going to have the same acceleration. Okay, because they have to move together. M2 can't move faster than M1 because that would require the string elongating. Okay, so now we can go on to set up our sum of forces. Okay, so what that's going to look like is we're going to have the forces on 1 and the forces on 2. I have, and these are the net forces on 1 and 2, so I'll make that clear. Net 1, net 2. Okay, and so I'm not talking anything about coordinates, or I'm not bothering to write x and y or anything because obviously it's all y for both masses. Okay, so what are the forces on mass 1? Well, we've got the tension force in the positive direction, so Ft, and then we've got the gravitational force Fg1. Okay, so those are the only forces acting on M1, and notice I have it negative because it's pointing downwards, being consistent with our coordinate axis. And then I'm going to have M1A. Not A1 because there's only one acceleration. It's just A. Okay, and it's moving, right? It's accelerating up. Okay, meanwhile, for mass 2, I'm going to have Ft pointing up minus Fg2 and then equals negative M2A. Why negative? Because we expect it to accelerate down. And now you might be thinking, well, what if I didn't make this assumption? What if I didn't have the intuition that mass 2 is going to go down and mass 1 is going to go up? Or, am I required to make that assumption? Well, no. If you don't make that assumption in your problem, then you're just going to get negative values, which will tell you that your assumption was incorrect. Right, so like for example, you could get a negative quantity of friction of the tension force if for some reason you assume the tension pointed down, right, which would be an odd assumption. But if you assume that A2 went up, right, and A1 went down, and then you went and you proceeded with that assumption, well then you're just going to get a negative value of acceleration, which just tells you that your assumption was incorrect. Okay, so now we're going to expand out our sum of forces, right, and not just write them so symbolically, but write them not with numbers yet, but just with more of what we know about the system. Okay, in other words, I'm just going to expand out the gravitational terms in this case. Okay, so what that looks like, then I have Ft, this is just coming from the net 1 equation, Ft minus M1g equals M1a. Okay, and then the other equation, the equation for mass 2, is going to be F2 minus M2g equals negative M2a. Okay, and we have two unknowns and two equations. Okay, so two unknowns, which are the tension force and the acceleration. Now we're going to use the tension force as a stepping stone to solving for the acceleration. And what that's going to look like mathematically is doing a substitution. Okay, so I'm going to solve for Ft using the equation for forces on mass 1 and then substitute that in to the equation of forces on mass 2. Okay, so I'm going to write that Ft is just going to equal M1g plus M1a. Okay, looks good. All right, and I'm going to substitute that in. Okay, so now I'm going to take this and substitute it in for my expression for tension. Okay, so we're getting rid of tension, having an equation that just has what we want in it, known quantities and our unknown acceleration. So M1g plus M1a minus M2g equals negative M2a. Okay, I'm going to collect like terms, put the g's and a's together. Okay, so then let's go ahead and add basically I'm going to subtract out the, or add an m2a to both sides. So I'm going to have m1a plus m2a. All right, that's going to be on the left-hand side of the equation. So notice I left the m1a by itself, and then I added m2a to both sides. And that means I want to get all the g's to the other side. So that's going to look like m2g minus m1g. Okay, looks good because I added m2g to the right-hand side, making it positive. I subtracted m1g from the left side and also subtracted it from the right side, making it negative. Okay? All right, so now it's just a matter of solving for a. So obviously I'll factor out an a from the left-hand side, and I just m1 plus m2. And I'm going to go ahead and factor out a g over here and get g of m2 minus m1. Okay, so then for our final step, we're going to get a equals m1 plus m2, all divided by, oh, and whoops, not quite, right? So I still have, in the numerator, I have g times m2 minus m1, and then all divided by m1 plus m2. Okay? And I'll even write m2 plus m1, keep it in the same order. Okay? All right, so symbolically, that is our answer, but we'll go ahead and plug in the values that we were given. Okay? So we want to plug in, just g and then 2.5 and 7.5. Okay, so we're going to have 9.8. Okay, and then open parentheses. Okay, and then m2 minus ma, so 7.4 minus 2.5. Okay, all right. And then divided by the sum, so 7.4 plus 2.5. Okay, plus 2.5. Okay, that's good. All right, and hit enter. All right, so 4.8 is our acceleration. All right, so 4.85. Yep, meters per second squared. Okay. All right, there you see the answer. Okay, so 4.85 meters per second squared. As I said before, and we can look here at the calculator, if I had assumed opposite directions in the acceleration, my numerator would have had a 2.5 minus 7.4. So I would have ended up with a negative, and otherwise the same value. I just said negative 4.85. Again, telling me my assumption was wrong, right? So it's a robust system. You can really, make any assumption you want because the math will tell you the answer. Okay, but since I assume these directions for acceleration, I get a magnitude, and that's how fast the system moves. Okay, so m1 is going to accelerate up at that rate, m2 will accelerate down at that rate, and notice obviously that it's smaller than gravity because it has to be. If you get an answer bigger than gravity, it's incorrect. You made a mistake with your algebra or somehow with your setup because it has to be, you only get gravity in the case of free fall, and here we have less than free fall. m2 is being impeded in its free fall by the need to lift up m1 as it falls. Okay, thank you.